So in this video I'm going to talk through topic 6 of P1, which is energy in the future, and it's a pretty straightforward topic. There isn't really too much content on it. It's mainly talking about Sankey diagrams and how to make Sankey diagrams work, but also talking about how systems can maintain constant temperatures and constant energies. Right, so just to quickly show you the areas that you've got to cover as part of the assessment. So list, it should say all 9 forms of energy there, giving examples of each. State the law of conservation of energy, okay. Draw a Sankey diagram for a specific situation here, so we'll come back to that once I've been through Sankey diagrams. Define a few terms, efficient, and also you've got to calculate the efficiency of this TV above over here. And then you've got to state the factors that affect how quickly objects radiate out heat energy, and state the conditions required for a system to maintain a constant temperature. Drawing some diagrams and giving examples will help with that. Right, so skip right to the end of this to talk through this. So our 9 forms of energy are here. So electrical, light, sound, kinetic, nuclear, thermal, gravitational potential, lesser potential, and chemical. That's pretty straightforward. Okay, so there are 9 forms of energy there, and you should be able to pick up examples of those pretty easily. If not, Bite Size is a very good list of examples of each of those, but I've got a few on there as well. The main ones that people sometimes make mistakes about are nuclear, which is about those that release from nuclear reactions, and gravitational potential, essentially anything that has the potential to fall. Right, so the conservation of energy, as a rule, conservation of energy states that energy can never be created or destroyed, it can only be transferred. Okay, so only moved from like one place to another, or transformed, essentially, changed from one form to another. So these transformations take place all the time. A microphone takes in sound energy, creates electrical. TV takes in electrical, makes sound, light, and heat. And possibly a bit of kinetic if it's got a fan in there. So we represent these energy transfer diagrams by using Sankey diagrams. These are drawn to scale. So however wide the box is, each box will have a certain worth, and therefore they're drawn to scale. So how many boxes come in on this side must be equal to the amount of boxes that come out over here. The efficiency is going to be the total energy transferred by the device divided by the device divided by total energy supplied to it. Okay, so for this toy car, we've got 20 joules of useful energy. So over here, 20 joules comes out as useful kinetic energy, and the total amount of energy that comes in is 200. I've got that over there. So you do 20 divided by 200, and you times that by 100%, so that ends up being 10% efficient. Efficient is about what percent of energy it uses usefully. Right. So moving on slightly before we go back to the assessment criteria. Thermal radiation. So objects give out heat based upon different amounts, different substances, different properties. Sorry. So dark matte surfaces are good absorbers and emitters. They're very good at giving out and very good at taking in heat. If an object is hotter than its surroundings, so that's 50 degrees C, and the surroundings is 30 degrees C, that will give out heat well. If it's colder than its surroundings, so that's 5 degrees C and that's 30 degrees C, then the heat will come in. That's when it will be a good absorber, when it's cooler than its surroundings. That's when it will be a good emitter, when it's hotter than its surroundings. That's how it can be both a good emitter and a good absorber. So wearing black clothes on a sunny day warms you up because the black absorbs thermal radiation. Also, the back of the fridge is black to emit heat energy taken out of the food. Light shiny surfaces are poor absorbers and poor emitters, so they're good reflectors. Okay, they don't. So kettles, after all, once they don't emit a lot of thermal radiation when they're hot, so therefore the water doesn't cool down quickly. Size and shape also has an effect. Larger surface area, faster emission. Okay, greater the temperature difference, faster emission. The greater the temperature difference, the faster the rate of thermal radiation is emitted. Some dull experiments can be performed to prove the fact that black dull surfaces are better absorbers and emitters. I hope you all appreciate that joke. It did take me a long time. So Leslie's cube is one of them. Okay, you've got a dark matte surface on this side, you've got a light shiny surface on this side. This side will heat up quicker. They'll both reach the same temperature. It's that this will get there quicker because it's a better emitter. Okay, so they reach the same temperature. It's just that this one does it quicker. This one over here, it's a light shiny surface. This is a dark shiny surface, dark matte surface. This will absorb the heat quicker, therefore this wax will melt faster, and that pin will drop off faster as well. The final point I just need to tie in is for an object to remain at a constant temperature, it needs to radiate power at the same rate that it absorbs it. So in other words, the power in needs to be equal to the power out. Think about a colander. If you want the colander to stay with a constant amount of water in it, the amount of water leaving the colander needs to be equal to the amount of water coming into the colander. Same idea over here. If you want something to stay at the same temperature, the amount of energy in needs to equal the amount of energy out. The amount of power in equals the amount of power out. Normally with a transformer, and we did about transformers in the last video, P equals IV, so power equals current times voltage. Current times voltage on one of them equals current times voltage on the other one, because we are not losing power. So current times voltage on the primary is equal to current times voltage on the secondary. Okay, let's just double check to see if there are any points that I've missed out on the assessment criteria. I don't think there are. Let's just bring this up a bit. Okay, so we have listed, not wrong one, oops, no, I just did have it there. Yep, we've listed all 9 forms of energy and given examples. We've talked about the conservation of energy. Sankey diagram, okay, so if it's 150 joules of energy, okay, that's how much is going to come in over here. 75 comes out as light, so that's half. 25, again you need to draw it to scale. The sound, and the rest of that 50 is heat. If it's drawn to scale, you can see the sizes perfectly. Okay, the efficiency, so remember it's going to be 75 or 25, so it's 100 divided by 150 joules times by 100%. I need to calculate what that value is. So that's that one there. We define the term efficient. You can calculate the efficiency of the TV, so that's that one over there. And we talked about the factors that affect how much heat is given out and the conditions for them to maintain a constant temperature. And that's the video on topic 6 of P1.